But thank you. I'd like to introduce now Elena Couce from Cefas.
Hello, everybody. And yes, so my name is Elena Couce, and I'm going to be briefly talking about thresholds in fish community composition. And so this is some work I've developed with Maury and with Michaela, which have also been here in this conference. And this is part also of pyramids of life. So basically, I'm looking at the fish data. And we've been doing fish surveys for a long time. So there is over like 40 years of fish survey samples in the Northeast Atlantic shelf. And they cover generally a very wide area, and they are very uniform over time. So it's actually a high amount of high quality data that is there to be analyzed. And so I'm only going to focus on the last 10 years of data because of the problem that David was just saying now, and that the high resolution fishing pressure data is only available for fairly recent, okay? But there is a lot of data. Even in that time, in those 10 years, there is 18,000 surveys. And so in these 18,000 surveys, we detected about over 60 fish species and 6 flatfish species. And we use 2 different gears, GOB and beam. So GOB is more shallow. They are both trolls, but GOB samples the fish over the seabed, and beam actually goes deeper into the seabed. It digs down. So we use beam data to study flatfish, and we use the GOB data to study the other fish. So we had 6, sorry, that's not what I meant. Oh. And yeah, we had 6 flatfish and 55 of the others. And we divided this in 4 size classes. So we had small juveniles, we had medium juveniles, we have medium adults, and we have large adults. Okay, you can see an example there of what it looks like. So we ended up modeling 182 combinations of species and size class. So we had 159 of the other type of GOB fish, and we had 23 flatfish. So we have all these fish surveys, and we know which species we found in each of these samples. And now we want to understand why. We want to understand why in some places we find some fish, and in some other places we find other fish. So this probably is related to some environmental conditions that are found in one site and not in the other. So we use a lot of environmental data, and this is mostly model data from Copernicus. And so yeah, things like bathymetry, temperature, the standard deviation of temperature in space and time around the site that we sample, the distance to coast, and the temperature difference between bottom and surface, so that measure the stratification of the water, the composition of the sand, mud, and gravel on the bottom, and total organic carbon, nutrients, oxygen, gross primary production, a lot of variables. And then we also look at anthropogenic stressors, and these are fishing pressure. And we use the ICES-OSPA international trawling activity, which is available from 2009 onwards, and it's high resolution, and it covers more or less the area we're interested in. And the method I use is called gradient forest. And in this part of the talk, many people switch off because they think it sounds complicated. I'll never understand it. So they just stop paying attention. And I promise, if you pay attention for 1 minute, you will understand it, because it's not complicated at all. I promise, honestly. If you don't, come to see me afterwards, and I'll apologize and give you your minute back or something. It's okay. So in order to understand what a gradient forest is, we have to start with a decision tree. And a decision tree, I don't know if you've played this game, Who is Who? Like you have all your suspects, and you have to start asking questions. Is it man or woman? And you just start dividing your data into, you start asking yes or no question, and you split your data. So this is exactly what a decision tree is. You just start asking yes or no question to split the data. And in the end, the hope is that you're going to arrive with uniform groups, okay? So there is mostly presences, mostly absences. So you can split the data, okay? So that's exactly what we do with a decision tree. And it looks very nice because you can put it out in a board and you can talk to it, and it actually makes sense from an ecological point of view. And it can deal with the interactions between variables. It can deal with missing data. It can deal with a lot of things. It's a pretty good model in one sense. It has one problem. If you want to use it to predict data, it's pretty rubbish, to be honest. I mean, is better than a random guess, but it's not that much better than a random guess. So in machine learning community, they call this a weak learner. Okay, I guess it sounds better than rubbish model, but it comes to the same thing. So what does machine learning community do with this? And they said, okay, no problem, you have a rubbish model, but instead of one, just use a few hundreds of these rubbish models that are just a little bit better than a random guess. And if you come to some average conclusion from all of them, then you end up with a pretty good prediction. Actually, I think this is like what is behind democracy, kind of, and you just have a lot of stupid models, and each one a little bit better than random guess. And if you combine the average prediction of all these models, you end up with actually, that's the hope, with a good prediction. I mean, it's based on the assumption that it's better than a random guess. That's where democracy maybe fails. So yes, that's what a random forest is you just randomize the process of creating trees, and you just average their results across all these trees. And both the tree and the random forest, they are used to study one thing, one individual thing. It's normally a species. Okay, in this case, I'm using it to study a species size class, but it's one unit. So what is gradient forest? Gradient forest is instead of having one, you're looking at one thing, you're looking at many things. So basically, instead of doing one random forest model, you do one individual random forest model for each thing you're looking at. Okay, we have 182 taxa size class, and I have one individual random forest model for each one of them. And then somehow I look at the result in a way that combines the output of all of this. So imagine each of these is a column, like here, and then you have this line that comes off. And you study the response of these individual lines to a stressor, in this case, temperature, okay? So this axis shows you temperature, and this is the response of your organism. And it's a cumulative response, so it's always going to go up. If you have a line going up, it means the organism is responding to that temperature. And if you have many lines going up, like here, for example, maybe there is a threshold, maybe the composition of the ecosystem is changing there. A lot of species are responding to this value. It could be that just by chance they all respond to the same value. It could be that one key species responds to this value and the other species respond to the key species responding to this value, but the ecosystem composition is changing in this value. So this is what I mean by threshold here. And that's what I'm looking for. I'm looking at places where a lot of these lines go up at the same point. So this is what it looks like in reality. So for all the variables. And you can see it's difficult here to say where there is a threshold. There is one beautiful threshold here. You can see that there are a lot of lines that are going up there. The black line is the average of all the blue ones. And so sometimes it's easy to see, sometimes it's complicated to see. There is this plot that helps you see better. And this is basically just looking at the number of splits, the distribution of the data, and the ratio between the splits and the data. And basically, when you have a high ratio, when the blue line is high, that's when you have a threshold. Okay, so you can see here you have a threshold, but there is other threshold somewhere else. So there is a threshold. Here there is a threshold. Here there is like a double threshold, a bit more complicated. Here you have a couple thresholds. So there are thresholds. You can find thresholds here. Once you know what a threshold is, you can map it in space. You can say these are areas that cross the threshold between 2005 and 2015. If you're a manager, that means that your community composition is changing there, and it's nothing you can do about it. It's not about fishing, it's about temperature. So that's important for you to know. What's happening here? Why is there a threshold there? It's basically because juvenile fish likes very warm water, and adult fish actually like colder water. So that's the composition we're seeing with the flatfish, the response we're seeing in this particular temperature. So what about trolling? Really, that's what we were interested in. Actually, trolling is not very important for fish community composition. This is just presence absence, it's not abundance. I'm looking at here. So you can see the importance of our variables, and basically the longer the bar, the more important it is. And you can see the fishing variables are right at the end. So that's not very important. And that's different to another study we did looking at the marine benthos. You can see beam trolling was quite important. It was up there. But for fish, I'm not seeing that. Okay. So that's a bit of a change. There is no obvious threshold here, whereas for benthos, we had an obvious threshold, and it was at 0. It was right at the beginning. If you look at the other plot, it is there. So, well, sorry. Yes, so unfortunately, I'm not seeing this here so far. So I have some ideas of how to develop this work further to maybe look at different time periods and different areas. And once you know how your community changes with pressures, you can map it in space. And you can see which variables are the one driving the change in all these places. So this is a principal component analysis we did for the GOV fish. for the bean and for the benthos for comparison. And we can see we can map it in space how the community is changing over time and which variables are the ones that are driving this change. Okay. And yes, I don't really have time to go on detail, just so you know that it can be done. And so the next step for the study, this is still some preliminary results. And the next step, I was thinking of trying to use a longer term fishing pressure data. We don't have high resolution, but we have some coarser resolution ISIS rectangle scale, and we had it for the North Sea. So I'm thinking of trying to use that data set, which is what we use for the benthos study. And we also could use for the EEZ, the UK EEZ, we have a very high resolution all gears data set, so also nets and everything. So I was also trying to use that and update the environmental data to something a bit better and maybe restrict a bit more the variables. So things like this is what I was thinking of. Maybe doing abundance instead of presence absence could also be something I can potentially look at. And yeah, the conclusions, just very briefly, sorry about. And yes, for management, you need to understand how your system is responding to both the pressures you can manage and those you cannot manage, because sometimes the change is happening and it's not really something you can control. And so that means that static targets for management may not be appropriate always. And yeah, I hope I've convinced you that gradient forest could be used to study this kind of systems, and it can actually give you some useful and relevant information. So thank you very much.
Thank you, Elena. And we